All right, this week we're going to talk about thunderstorms. What we've been doing is coming down scale. In other words, smaller and smaller events that impact the weather. We started out looking at planetary circulations, then we went to the mid-latitudes where we live, and now we're going to come to a part of that thunderstorms, mesoscale circulations. Each one of these interacts with the other as they work their way together. However, thunderstorms are something that's interesting and have a major impact on our lives at times. They can produce extremely bad weather. They can produce very heavy rain, and sometimes they produce just beneficial rain. People in Florida, for example, needs a good tropical thunderstorm season during the summer months to maintain their amount of moisture they need in the soil to keep it going throughout the year. So I wanted to just start with a current radar. And instead of looking at reflectivity, I'm looking at precipitation estimates. Notice there's some different colors, especially across the Dallas-Fort Worth area. This is heavier rainfall for the last hour, upwards of an inch, almost 2 inches of rain in the last hour in that area. This is convective rainfall. You do not get this kind of heavy rainfall without. However, this can be part of a front, which is synoptic or mid-latitude scale. So what happens is we're looking at smaller scale enhanced vertical motion. So this is an example of that rainfall occurring right now, picked up by the Doppler radar, a dual pole radar. So it's enhanced to improve the amount of information it has on the QPF, or quantitative precipitation estimates that occur. If we were to look just at reflectivity, here you would just see a enhanced, because you get more drops, you get more return. So you get more of the yellow into the red during across this area right now. If we were to look at the upper air that went with this, and this is just an example of upper air soundings down here in part of the world, take a look. Cold air is at the bottom. Very cold air actually is the cold front down here. But look at this aloft. This is the amount of instability. If we can get a parcel to lift right here at 850 millibars, we wind up having a fairly unstable atmosphere. And that is what's happening down there. You don't always have stability. You don't always have the instability caused by the temperatures that getting too warm at the surface. Sometimes aloft, especially in the Midwest, you can get thunderstorms. And this is what is going on here. You're getting a lift due to a front, and you look at 850 millibars, you see good moisture transport into that area from the south, lifting over the front. So all of this is generating those thunderstorms. So now let's just go look at those thunderstorms. Look at a little bit more detail here. And we'll talk a little bit about thunderstorms and how they form and the various aspects of them. So, starting with the beginning of thunderstorms here and tornadoes, what conditions in the atmosphere favor it? So we're looking for an enhanced vertical motion. So we want something to bring up the vertical motion quicker. We have here a good strong updraft. We talked about parcels of air. Well, 3 to 5 kilometer parcel of air here going up. It continues going up until some of it gets too heavy from the water and begins to sink back down. The rain begins to fall. That pulls the air back down with it. It cools the air because of evaporation, so it becomes denser, so it actually becomes more stable, so it falls back. And if you had just one thunderstorm cell, this is what would happen. However, we don't typically. We have single cells like that many times occur in the summertime. We can get multi-cells, a line of them, maybe a supercell. So interestingly, thunderstorms develop, and there's something uh, interesting that happens. In other words, they develop, say, on the southern end of a line. As that line is moving along, they reach a stronger intensity, and then they gradually dissipate. Well, a new cell develops on the southern end of the line again, replacing these old ones. So instead of getting a nice northeast motion, you wind up with an east motion because you have continual redevelopment on the south side of the line. So while the actual individual cells are moving to the northeast, the thunderstorm cluster is actually moving to the east. What conditions are we looking for? We're looking for a maritime tropical air mass, and that can be aloft, above, as I showed you, a cold air mass at the surface. We definitely need instability. So solar heating will help. Interestingly, low-level jets, particularly at nighttime in the Mississippi, Missouri River Valley, contribute to a nocturnal thunderstorm maximum there. In other words, where I was showing you in Texas today at Dallas area, if you were to take that same area and project it due north, sometimes, especially during the wintertime, springtime, and fall, they get a nocturnal jet that develops in this area. In other words, a low-level jet around 5 to 10,000 feet out of the south. And along this jet, it's transporting moisture above maybe a cooler air mass, and it's causing thunderstorms to form. Here's the actual thunderstorm days, and notice Florida is the winner. But everywhere in the U.S. gets some. Notice Hawaii doesn't get a whole lot. Why the heck does Hawaii not get much? They're surrounded by warm ocean. They're in the tropics. They have strong sunshine. You would think that everything points to Hawaii getting at least as many. They have mountains. So you would think the lift there alone would give them tremendous amount of thunderstorms. Well, guess what? They're in the tropics. We talked about an inversion, a trade wind inversion. Well, the Hawaiian Islands sit right where that trade wind inversion is. They cannot get the lift to go higher than showers. They do not get that cold thunderstorm top like Florida does. Florida does not have that inversion. And Florida has sea breezes coming from both the Pacific, the Atlantic, and the Gulf of Mexico. When they meet together, that's where the thunderstorms pick up. I got caught by that when I first went to Florida State. I did not know what I was doing as a meteorologist yet. I was still learning. And I was outside first couple days on campus, and I could see to the east these big, big clouds. Thunderstorms, definitely. And I thought, oh, they're east of me. They're not going to come back here. Well, in Florida, depending on which sea breeze is winning, and that day the Atlantic one did, the thunderstorms moved west right over where I was. I got soaked. I learned a big lesson that when you down in the tropics or a little closer to the tropics, thunderstorms can move from east to west. One of the biggest things about thunderstorms is wind shear. Severe thunderstorms. You notice the definition of the Weather Service. It has 58 mile per hour winds and hailstones greater than 1 inch. There is nothing in there about lightning, how much lightning with a storm. And thunderstorms can also produce fast floods. Vertical wind shear. We've talked about vertical wind shear before. We've looked at it in the sense of wind speeds changing direction with height. Well, you need vertical wind shear to keep the updrafts going. In other words, the strong wind shear will help to keep that updraft from cutting off all that warm, moist air that thunderstorm needs to grow. If that happens and it gets cut off, the thunderstorm is going to die. This is an image, and you're going to see it in some of your critical thinking this week, of what is the synoptic weather pattern in the Midwest that causes severe weather. Upper plains, lower plains, whatever you want to call it. What you have is a very strong developing extratropical low. Where's that low? Usually Nebraska, maybe Oklahoma, maybe Kansas. With that, you have a strong upper level jet. We know you need the jet to get divergence, so that's what forms the low. Out of that low, you have a warm front and a cold front. All extratropical lows do. So along the cold front is a very steep surface, pushing the air up. Along the warm front, you have gradual, you may actually have a large area of rain north of it. And then you break out once the warm front passes you and you get partly sunny skies. Maritime tropical air mass coming in. Lots of moisture, lots of higher temperatures, a low-level jet. Notice the wind shear. Southwest winds, southerly winds. You have very strong wind shear. All of that are perfect ingredients to force very strong lift, very unstable air, severe thunderstorms, because you have the strong wind shear to maintain the severe thunderstorms. So, interesting little lightning. Lightning you would think lightning was caused by air moving against each other. I always thought that originally, but lightning is not really that way. Grapple's like a mix of ice and water, kind of a mix of two. If the temperature is less than 5 degrees, grapple becomes negative charged and ice crystals become positively charged. However, if you flip it and you go down to near the base, then you have positively charged grapple and negatively charged ice crystals. That is why you get opposite charge based on temperature are causing there to be a large difference in charge and allows the lightning to occur. That is what you're getting your lightning from. So one of the key things, if you look at lightning, if you're getting lightning in a thunderstorm, means the temperature in that thunderstorm is at least below -5 degrees Celsius. If you knew what the temperatures were in the vertical, you could tell at least how high that cloud was. Interestingly, there are strong winds that come down sometimes in the thunderstorm where the rain shaft is. Think about it. Rain is a cooling process. The evaporation is occurring around that rain. It's cooling the air. That air is much cooler than where the main updraft is. That air is stable. What happens with stable air? It sinks. You also have the drag of the rain pushing down. All that comes down and hits the ground. Sometimes not a big deal, maybe 10, 20 mile an hour wind. Sometimes a very big deal. Wind gusts can exceed 170 miles an hour in some of these downdrafts. If you're an airplane, think about it. You're coming into the downdraft. If you're coming one direction and you're going to have a very strong headwind, helps you fly better, right? But once you go to the other side of the downdraft, you have a very strong tailwind. There are also bow echoes and derechos that develop along the line of thunderstorms that have good wind shear. Derechos are long-lived, at least 240 miles they travel. They can come across the Midwest. They can come across the East. Several of you, as one of your memorable weather events, actually talked about derechos. They develop more in the plains and then track to the east. They're mesoscale convective systems, which means they have some good wind shear, and they have a series of thunderstorms that keep developing and then propagating eastward with time, or southeastward. And here you can see how they ordinary thunderstorm, a few more develop, it gets more and more bowed, and you wind up almost looks like a low pressure up here, doesn't it? And in some ways it is. And many times you'll have severe weather close to the 1 comma head to the north and at the bottom of the comma head to the south. And here you can see some of the derechos that have occurred. And you see some have moved across your Ohio, West Virginia, down to the southeast with time. Another part, think about it. All this moisture is being pulled in. You need a tropical, semi-tropical air mass anyways for good thunderstorms. You wind up with tremendous rainfalls. Many cities can't handle 2-3 inches of rain in an hour. That is a 100-year rainfall event for some areas. I was in Tucson, and we only had a ½ inch in an hour. Tucson doesn't get that. They typically get 2/10 of an inch, maybe at most, in an hour. We had flooded streets everywhere. And This heavy rainfall can occur up at the end of a canyon, and Big Thompson Canyon was a classic example. So mountains, rivers don't necessarily have to have the rain on them. They may have it on the headwaters of that area. Hail is another part that develops in thunderstorms. And we need at least quarter-size hail to be considered severe. Interestingly, dual-pole radar is a great tool for picking out hail. It can pick out a difference because it looks at shapes, a two-dimensional shape, and with that it picks out the difference in hail. You can pick it up aloft and actually watch the hail shaft come to the ground. Tornadoes are another part. Very strong updrafts pull in a tremendous amount of air, create very low pressures. Interestingly, tornadoes can track for very long distances or maybe just very short distances. There's a tornado alley out in the Midwest from Texas through Nebraska, and there's a secondary area called Dixie Alley over southeast United States. You need really strong wind shear, and you're looking at supercells. These are cells that instead of being part of a line, maybe out ahead of it or off from it somewhere, they have good flow of moisture into them. They maintain themselves, and they start rotating. That rotation is what Doppler radar picks up. When it sees that rotation, you know you have the potential for severe weather. Maybe it'll be hail, maybe it'll be tornadoes. And that is where the key determination has to come in. Here, as you can see, the number of tornadoes per state. Notice the size of the states, depending on the states. Interestingly, per capita, for number of population or for area, Oklahoma, Mississippi, Alabama, and all are right up there. Even Texas, even West Virginia does have tornadoes. And this is the annual per square miles now. This was a Doppler tornado which occurred was an EF5. We have an enhanced Fujita scale. All that is we look at the physical damage using engineering specs. We can determine the speed of wind that caused that kind of damage. And this was Joplin tornado. Actually had a very good warning out, almost an hour lead time in some areas. So I hope you get a little bit out of all this, and let me know if you have any questions.